All right, so we're on the part for the definition of the definite integral, and the definition of the definite integral is right here. So if you can just copy all these notes at this time, I'm gonna break this what these notes mean. But so here we go. Let me draw a general curve for us. So what this means is, let's say we have an interval a to b, and we have an area under the curve. That's what this guy means. Okay. Whenever you see an integral sign, that means the area between a and b of the function f of x. So if this is f of x, what it's basically saying is this symbol right there is the area under the curve. Okay, area under the curve. And how this area under the curve, this definition of a derivative, is defined as this whole weird thing. Now, it looks crazy right now, but if we break it down, it'll make much more sense, okay? So that's what I'm here to do at this time. So this f of x is an irregular curve, and it's not very easy to figure out the area under it. But what we can do, just like we did in the previous problem, is we can break it up into rectangles. Rectangle 1, rectangle 2, rectangle 3, rectangle 4, right? We can keep going. And this will help us find an area that's pretty accurate, right? But it's not perfect. And so to make it more and more accurate, what we would need to do is make smaller rectangles, essentially, right? We'd get smaller and smaller or I don't want to say smaller and smaller, but very small equivalent rectangles. Okay, and that's how we would get more accurate, right? So let me just kind of just draw a little bit bigger just to show you what I'm talking about. Okay, so to find the area under the curve, what we would do is find the area of the first rectangle, the second rectangle, the third rectangle, and until until the last rectangle, right? And to find the area of this first rectangle, we need the height times the width right there. And so that's what up here is all talking about. This f of x1, that's here is our first x coordinate, x value. So this right here is your f of x1, right there. That's the height. And right here is your delta x. Your height and your width. All of rectangle 1, or area of 1. And so you keep going. This is the rectangle 2, rectangle 3 area, keep going until the final rectangle, right? So that's what it means. And like we said before, to be more accurate, we don't want big rectangles. We want small, tiny rectangles to be more accurate to the curve, right? And that's where this idea where n, representing the number of rectangles, approaches infinity, right? Hint, limits. When we have n approaching infinity, this helps us become more and more accurate. Okay, more accurate as we approach infinity. So that's what all of this can be represented in this notation, summation notation. So let's kind of break this down, okay? I'm going to show you how this works. So this is equal to the limit as n approaches infinity, because that's how we get more and more accurate. How does summation notation work? We take our first value, 1, and we plug it into our function here. So we have f of x1 times delta x. So there's our first term. Plus, now what happens to this 1 here? It changes to a 2 then. So now we do f of x2 delta x plus, and then the next one is 3, f of x3 delta x. When do we stop? We keep going until f of x, what? The final number n right there, delta x. And do you see how what we did is we just created the statement right above, right? So that's what this whole thing means, okay? So just to give a summary, the area under the curve will be accurately represented by rectangles, the sum of all the rectangles when you have your rectangle width very, very small, or if you have more and more rectangles, okay? That's what this means. Now just here's a sub point. We got to make sure that our function is continuous, or else we can't do Riemann sums, okay? That makes sense. If you have like a jump, that's how do you find the area under, right? It's like you can't really find the area of a non-continuous function, okay? And here's a little helpful point. Just want to give you another tip. So if you have an interval a to b and you have n subintervals, then you can find that the width is equal to this formula, okay? Now let's kind of remind ourselves of a previous problem right here. We had intervals a to b of 4 subintervals n, and so what we found that was that the width of each rectangle was 0.5, and we can do that by finding the total distance. So the width is the total distance b minus a over the number of rectangles, right? What's the distance between 1 and 3? It's 2, right? 3 minus 1 equals 2. But we want to divide it into 4 parts. Hence the 2 over 4 is 0.5. Okay? So that's what this is. It's very helpful to help us figure out what each width is going to be of each rectangle. And there you go. This is the definition of the definite integral.